Rolle's theorem. Objective: use Rolle's theorem to prove the existence of a horizontal tangent to the graph of a function. This is an existence theorem. Rolle's theorem says, let f be a function defined on a closed interval from a to b. If f is continuous on that closed interval a to b, f is differentiable on that open interval a to b, and f of a equals f of b, then there exists at least one number c in the interval a to b where f prime of c equals 0. Meaning there is at least one location on the graph if in the given interval where the tangent line is horizontal. Now let's take a moment to explore this. We're going to try to draw a function that has the following characteristics. It is continuous on a closed interval, so we never pick up our pencil to draw it from endpoint to endpoint. It is differentiable on the open interval, so it is smooth and curvy. Well, at least it is smooth. There are no sharp points. And the endpoints of the interval have the same y values. So, same y values. Wherever we start the function, we have to come back to that point, making sure I never pick up my pencil. I'm drawing smoothly, no corners, vertical tangents, things like that. The endpoints have the same y values, so where I started is level to where I stop. I could go up and simply just come back down. I could also stay at the exact same place the entire time, as long as the beginning and the end have the same y values. Rolle's theorem tells us there has to be at least one location on any of these functions where the tangent line is horizontal. Notice on this one, this spot right here has a horizontal tangent. This spot right here has a horizontal tangent. There are two places. This spot right here has a horizontal tangent. On this one, it is a horizontal line, so the derivative equals 0 everywhere. So of course, if we start and stop at the same y value, no matter where we go, as long as we don't pick up our pencil and we make a smooth connection, we have guaranteed that there is at least one place where the tangent line is horizontal, at least one place. Again, this is an existence theorem. It proves the existence of a location where the derivative equals 0, where a tangent line is horizontal. It doesn't necessarily tell us what that location is. It just proves that there is a place that exists that has that characteristic. Let's practice using Rolle's theorem. Examples. Number 1, verify that the function satisfies the conditions of Rolle's theorem on the indicated interval. Then find the number or numbers, C, guaranteed by that theorem. So there are three conditions that have to be satisfied. Now I notice this function is a polynomial. Since this function is a polynomial, it must be continuous and differentiable on all real numbers. So we write, since f of x is a polynomial, it is continuous on the closed interval, -2 to 2, and differentiable on the open interval, -2 to 2, since of course we can't take the derivative at endpoints. Now the third condition is that the endpoints have the same y values. Or f of a equals f of b. Our endpoints are -2 and 2, so we plug those in. Let's see. F of -2 equals -2 to the 4th minus 2 times -2 squared. That makes 8. And f of +2 equals positive 2 to the fourth minus 2 times positive 2 squared, which also equals 8. Therefore, f of negative 2 does equal f of 2, and the three criteria of Rolle's are verified. Satisfied, we verified that they are satisfied. So we can say, because these are satisfied, therefore, Rolle's theorem guarantees that the derivative at some c equals 0. The derivative equals 0 for some c on the interval negative 2 to 2. Now, the second part of our direction said to find the number c guaranteed by the theorem. So let's take the derivative of f of x, f prime of x, that's 4x cubed minus 4x squared, and, 4x, and set that equal to 0. Factoring gives us 4x times x squared minus 1 equals 0, which gives us x being 0, 1, and negative 1. So these c values guaranteed by the theorem are 0, 1, and negative 1. Example 2. Two students run in a race, starting at the same time and finish in a tie. If f sub 1 of t is the position of one student at time t, and f sub 2 of t is the position of the second student at time t, show that at some time during the race they have the same velocity. Remember that the velocity is the derivative of position. We'll say v equals p prime, or in this case, because we're using f for position, we'll call that f prime. Let's let the time interval be represented by the interval a to b. So they start running at time a and running at time b because they run at the same time. The position at the start time is the same. Therefore, f sub 1 of a equals f sub 2 of a. Bringing both of these to the same side, subtracting f sub 2 of a, that leaves us with f sub 1 of a minus f sub 2 of a equals 0. Also, at the end, it's the same position. So f sub 1 of time b equals f sub 2 of time b, and doing like what we did in the first one, f sub 1 of b minus f sub 2 of b will equal 0. Notice that at that time a, the position equals 0. At that time 2, the position equals 0. Let's call f of t the difference between those position functions, f sub 1 of t minus f sub 2 of t. Well, position is continuous and differentiable, and the position at the beginning is equal to the position at the end. F of A equals F of B. Rolle's theorem tells us F prime of t, which equals the velocity, is 0 for some time point on the interval a to b. So we've proven that at some time during the race, they have the same velocity using Rolle's theorem. Thanks for watching.